So good evening all. Today is the week 8 lecture lecture series overview session. So in the week 7 lectures we studied about the different mechanisms of grain refinement, in which we studied the carbide theory, peritectic theory. So uh, coming to so forwarding that, we will study some more theories on the grain refinement mechanisms. So let's start. So in the grain refinement mechanism, in inoculation process, first is the carbide theory, second is peritectic theory. So in the carbide theory, the some carbides are beneficial for the grain refinement, means they allow the low interfacial energy surface for the heterogeneous nucleation to happen. So in that, the AlB2 boride is good for the heterogeneous nucleation, while TiB2 is not preferred for the carbide theory heterogeneous nucleation. In the peritectic theory, the Al3Ti particles that are intermetallic phase in the aluminum system provide the formation of uh, aluminum nucleation uh, before the solvus line. Sorry. So if we write the equation, alpha is the, so this is the liquid plus Al3Ti particles that gives the alpha aluminum nucleation. So this reaction only takes up at the 665 degrees Celsius, and for a combination of 0.15% titanium. So this is the limitation of this theory. So in which early nucleation of aluminum allows the grain heterogeneous nucleation, leading to the grain refinement of the alloy of the microstructure. So next theory, third, is the peritectic help theory. In peritectic help theory, it is said that we know that Al3Ti provides the heterogeneous surface. So the intermetallic particles also dissolves, can also be dissolved with time, as the temperature of the cold liquid is still high. So if with prolonged time exposure, the intermetallic particles sometimes can also dissolve in the matrix. So the dissolution of these particles has to be prevented for maintaining the grain refinement. It has to be prevented. So how it can be prevented? Like the TiB2 particles which form in the aluminium, titanium and boron master alloy addition. So TiB2 particles surrounds the Al3I particles and form a shell around the Al3I particles and secure them to avoid the dissolution. So TiB2 particle form shell around Al3Ti. As the TiB2 the melting point of the TiB2 is very high, these titanium boroid particles will prevent the dissolution of the Al3I particles. So the as the Al3I Ti particles dissolve with the as the process proceeds, leave behind a liquid of peritectic composition inside the boroid shell. With time. So the limitation of this process is the first is the grain refining efficiency decreases with increasing number of melting and solidification cycles. Means grain refining efficiency decreases with increasing number of solidification and melting cycles. So how the grain refining efficiency decreases with increasing number of solidification and melting cycle is that as this allow the diffusion of titanium out of the bulk and prevent the peritectic reaction. Means the repeated solidification and melting of the Al3I particles will lead to the diffusion of titanium out of the bulk and prevent the peritectic reaction. As the peritectic reaction helps in the early nucleation of alpha aluminium nucleus. Second limitation is that it cannot explain the recovery by stirring process. Stirring process. Why stirring process? Because in the stirring process, the settled Al3Ti particles will again merge into the will again disperse in the bulk and provide the heterogeneous nucleation sites. Can be suspended again uniformly. Next theory is the hypernucleation theory. In hypernucleation theory, it is said that the titanium segregates at the boroid or melt interface that will restrict the mobility of aluminum atoms in the liquid. Segregates at boroid or melt interface and restrict mobility of aluminum atoms. That lead to formation of pseudocrystals. So these pseudocrystals act as nucleus for further grain growth. So we will see how this theory works. Like if this is the titanium particle, titanium atom, and it is surrounded by aluminum atoms, means Al3I particle. So next layer of atoms will be different. Like this. We will represent it by double dash. Yeah. So a boundary will be created around this. So the green boundary is the probable extent of restrained interfacial atoms. The second layer of atoms we will draw as it will like this. So the boundary around this will be the green. Okay. So this green boundary is straight, not the dash, while the blue boundary will be dash. This is straight. And the blue line is the conceivable maximum extent of stabilized region. So in this process, the center atom is the titanium, atom with cross is the aluminium atoms that are fixed by titanium. The atoms with double dash are the aluminium that are restricted. Rex in mobility. So this is how the pseudo crystal forms. First, so the titanium. So if we take a cross section along this is A plane. So when we draw the A plane, so the surface of this A plane will be titanium boroid substrate interface. So similar atom configuration will be here. So this is titanium. the solid boundary, and the outer dashed boundary will be like this. So atoms in this position will be same as in this initial process. So in this way, the titanium segregates at the boroid surface and forms a region which restricts the aluminum atom's mobility and form a pseudo-type crystal. So the pseudo crystal will act as the nucleus and grow in size. Means more and more aluminum atoms will start to stick on this. Means addition of more aluminum atoms will lead to the growth of these pseudo crystals with decreasing temperature. So how the this hypernucleation theory works? So for this to happen, the these solute atoms of similar size should be there. Of similar size as aluminium. Means solute atoms radius should be similar as aluminium atoms. That will only promote the hypernucleation. As the aluminium radius is 0.053 nanometer. While and also the nature of the solute atom also affect the hypernucleation, as the titanium is the best for hypernucleation process, while zirconium and chromium, they prevent the formation of pseudocrystal. Means prevent hypernucleation. Next theory is the solute theory. So in this both nucleants and segregating solutes influence grain refinement. So in it nucleants means the nucleus formed, and segregating solutes influence grain refinement. So the extent of segregation of nucleates and solute atoms is given as the grain restricting factor. Growth restricting factor. So the GRF, that is growth restricting factor, is given by a formula or the number of so if we write the number of grains per unit volume, number of grains means nucleating grains, by NVG, and number of particles per unit volume NBP. So the number of grains per unit volume increases with increase in number of particles per unit volume, only up to a critical value or up to a critical grain size. So if we draw a curve between n number of particles and number of grains per unit volume, so we can, this is 1 times 1. This will be 10 raised to power 2 or 10 raised to power 4. So initially it increases the number of nucleating grains number of grains per unit volume increases with increasing number of particles and saturate after reaching a certain grain size. So after saturation, the segregating particles do not act as nucleation sites. Means beyond saturation, segregated particles will not act as nucleation sites. And for the finer growth, for finer grain size, the growth restricting factor should be high. Means growth restriction should be there. So if we see the relation between growth rate and growth restricting factor is they relate inversely. Means for high growth restricting factor, the growth rate will be low, and the GRF is given as MC0 K minus 1. So here M is the slope of liquidus line, C0 is the solute concentration in melt, and K is the equilibrium partitioning constant. That is given as K equals to Cs by Cl, where Cs is the concentration of solid so this is solid composition, and this is liquid composition. So the segregated titanium has the high tendency, high segregation tendency. Means high growth restricting factor. That's why the grain refinement is higher in the titanium addition. So for the GRF values for peritectic reaction, peritectic composition, will be like for titanium it is 31, for zirconium it is 5, and for chromium it is 0.5. So here we can see that the zirconium and chromium has less growth restricting factor. Similarly for 0.01% titanium addition, the GRF for titanium will be 2.1, and for the 0.001% boron, the GRF of titanium will be 0.02. Means boron can restrict the segregation of titanium atoms. Next theory is in grain refinement is the fading and poisoning. Fading and poisoning means the decrease in nucleation rate and loss of, and the grain refinement efficiency decreases with time, and it is lost with after some time. Means the grain refinement efficiency decreases and lost after with the time. and poisoning means the stop preve- stopping of the grain refinement efficiency. So if the solubility of titanium in liquid aluminium is very less, means up to 0, the titanium solubility in aluminium is 0.25% maximum. If the concentration of titanium is very less, 0.01% titanium, the Al3Ti particles are not stable and dissolve with time, and leading to fading of the grain refinement efficiency. And the dissolution rate will, so the dissolution of these particles and depend on the holding time. Then the grain refinement efficiency will lost if the L3I Ti particles dissolves. With the long time holding time period, the Al3Ti particles can also settle down but this effect can be prevented by the stirring of the melt. Can restore grain refinement efficiency. So if we draw a curve between grain size and holding time, log scale of holding time, we see a decrease in grain size with time, and after some point it will start to increase, the grain size will start to increase again with the time. So this time is called the TC, critical time. So it not critical, it is contact time of the particles and the melt. And after TC, the all particles got settled down. So this effect is due to fading. If the melt is stirred, so the grain size will again start to decrease and increase after some time. So this recovery in grain refinement efficiency is done by stirring. At this point of time, when stirring is due, the grain refinement will start to recover. So the TC is the contact time elapsed between addition of master alloy casting process. And the minimum grain size that is achieved is written as the ultimate grain size. UGS is the ultimate grain size. So next is the poisoning theory. So there are some elements in the melt that restricts the grain refinement. Those elements are chromium, zirconium, lithium, and silicon. A very high level of silicon. So these all elements adversely affect grain refinement. Process. Leading to coarse grain size, compared to the grain size that will be obtained in the absence of such elements. So the coarse grain size is coarse as compared to where in the absence of these elements. So how this poisoning work? So mechanism of this is sorry for the interruption. So mechanism poisoning works as the if zirconium is present, it forms the ZrB2 intermetallic, and ZrB2 coat over titanium boroid particles. So by coating of this zirconium boroid on the titanium boroid, the grain refinement ability stops or lost of this titanium boroid. Or if it substitutes for titanium, it means if zirconium substitutes titanium and forms the titanium zirconium boroid, it changes the lattice parameter. So this boroid forms has the changed lattice parameter that will have the high misfit with the aluminum atoms and prevent the and decrease the grain refinement efficiency. So the grain refinement efficiency altered because of the formation of titanium zirconium boroid. Zirconium can also replace titanium from the particle liquid interface that lead to pseudo and the presence of this zirconium, chromium and silicon leads to the formation of complex aluminides boroids or silicides. Which do not have any grain refinement and grain refinement efficiency. So how can the grain refinement by other means is grain refinement efficient? So these are the grain refine limitation in the element addition of in the grain refinement process. Next is the how grain refinement is achieved in melt inoculation by other meanings. Grain refinement by mechanical or electro, so it can be also done by stirring process, vibration. It can be done by mechanical stirring, electromagnetic stirring, and third is the bubble mixing. So in the stirring process, mechanical stirring process, a physical stirrer is introduced in the melt, and rotated by a motor. So the stirring in mechanical stirring generates a shear fracture mechanism. In shear fracture mechanism, shear force generated because of the mechanical stirring breaks the dendrite arms. Shear force caused by stirring of viscous liquid means melt. So the shear force generated in this process lead to the fragmentation and breaking of the dendrite arm. Dendritic arms means, as we see in the solidification process, at the mold surface the small grains generates and that will grow as dendrites in invert the melt. So these fronts of dendrite will break and fragment due to mechanical stirring process and lead so in the stirring process the broken dendrites disperse through the melt and provide heterogeneous nucleation sites nucleus for grain growth. So in the mechanical stirring process only some different mechanisms work. Look, in the first is the grain boundary infiltration. In grain boundary infiltration, the liquid liquid and solid interface will create a liquid infiltration in the stirring process. It grain boundaries induce plastic bending of dendrite arms. So when the grain boundaries orient with the angle greater than 20 degree, so when grain boundary misorientation increases about 20 degree, means due to the infiltration process and a plastic bending of dendrite arms, the grain boundary misorientation goes beyond the 20 degree angle, that lead to the increase in grain boundary energy. So grain boundary energy increases about the increases 2 times higher than solid liquid interface facial energy. So the relative in the filtration process, the relative motion of liquid and uh, solid phases lead to the uh, formation of a curvature. Like if we see two solid regions, one grain, this is solid, and above this is liquid. So the surface energy of this curved surface, and so the surface will be gamma, can be written as the gamma SL, and the surface energy between two grains can be referred as the gamma SS, and the angle between this two curved grains is represented as phi, and phi is the dihedral angle. So the relation between interfacial energies between solid liquid interface and grain boundary energy is written as gamma SS equals to 2 gamma SL cos phi by 2. So in this relation, if dihedral angles decreases and goes to 0, the value of cos phi by 2 will be 1. That will lead to the relation of gamma SS equals to 2 gamma SL, means the grain boundary solid interface energy is much higher, 2 times higher than the solid liquid interface. So this formation lead to the breaking of dendrite arms. So this increase in grain boundary energy above the solid liquid interface lead to detachment of dendrite arms. From their mother grain. Means in this picture we can see that this is two solid grains. So the solid liquid interface is this, and this is solid. So if this energy exceeds over solid liquid interfacial energy, the dendrite arms will detach from the mother grain. The next mechanism in this is the remelting of dendrite root. Means the dendrite forms with the multiple arms. Like first this is the primary arm, next will be this secondary arms nucleating from the primary dendrite, secondary dendritic arms. So at the root of this secondary dendrite arms, the some ripening and due to the induced ripening and stirring effect, the solute segregates at these dendrite roots, near the dendrite root. Means due to stirring process, solute segregates at the dendrite root so the segregation of solute near the dendrite root lead to the decrease in melting point of that in that region, leading to decrease in melting point at that in the region at the root. And the curvature existing at the dendrite root also affect the curvature at the dendrite root also decrease the melting point of that region. So the decrease in temperature near the dendritic root is given as the R2Tm V sigma divided by delta Hm. So here V is represented as the molar volume, sigma is represented as the solid-solid interfacial energy, delta Hm is the molar heat of fusion, enthalpy of fusion. And R is the radius of curvature. At the root, dendritic root. So the fluctuation produced by the stirring process lead to the temperature and composition changes near the dendritic root, which leads to remelting of the of that dendrite arms. Means in this position here, due to stirring process, the composition and melting point in this localized region changes due to stirring process that lead to the melting of this arm. That so the broken secondary arm will be free, and in the stirring process after that will lead to the heterogeneous nucleation, act as the heterogeneous nucleation further because of the remelting of the secondary dendrite arm at the root. So next process is the crystal rain. So due to stirring process, as in the initial process of solidification, solidification, the e- the nucleus of small nucleus forms near the mold walls, and as the near the region of the walls, the solid phase concentration is higher than the liquid phase. So due to stirring process, the solid phase phase detach from the mold walls and start to fall in the liquid. And this can the falling of solid phase is also due to density difference, because the density of solid phase is higher than the liquid phase is high than liquid starts to fall in the liquid, and so the number of solid phases is much higher that it looks like a crystal rain in the liquid liquid melt. So the crystal rain leads to the very high increase in grain refinement efficiency. So the falling solid phases or solid phases or nucleus of grains can remelt because of heat flux in the heat flux of the liquid, or can grow. Next mechanism is the ultrasonic cavitation. In the solidification process in the liquid melt, some bubbles are also present because of the gases entrapped in the melt. So the clustering of these bubbles lead to collapse of these bubbles and produce, so the means the making cluster making growth and sudden collapse of big bubbles. Generate a cavitation in the liquid and provide a much higher pressure for on the melt layers of high pressure on melt for a short time. So the generated pressure lead to the enhancement of nucleation rate, that enhance the nucleation rate. And fragment the, it also fragment the dendrites. The generation of high pressure leads to pressure decreases the activation energy, nucleation, means because the activation energy is low in because decrease, so it will lead to more nucleation of particles. The high pressure generated also leads to break of cluster particles, means cluster particles, if it breaks, then will provide more heterogeneous sites and increase melting point of melt near collapsed bubble. So effect providing the effective supercooling, high supercooling. So the high supercooling will also lead to high nucleation rate. Next process is the electromagnetic convection. So due to the electromagnetic stirring effect, the magnetic field generates a Lorentz force in the melt or the melt liquid. And strong convection. So the generation of this Lorentz force and strong convection leads to the much more fragmentation of dendrites, and the nuclei will also swept away from mold wall. Swept away from the and disperse uniformly in the melt. Providing the high nucleation. And growth leading to finer grain size. So these are the different types of grain refinement mechanisms by different types of meanings. Like first is the melt inoculation, in which some elements are added. Second is the mechanical stirring. Second is crystal rain, ultrasonic cavitation. And the so first is the I will mark this like electromagnetic convection process, the ultrasonic cavitation, crystal rain. These are the different grain refinement mechanisms because of the stirring process. This is the grain boundary infiltration. this is due to curvature present at the dendrite root, leading to demelting of secondary arms. So bubble mixing also seen by the ultrasonic cavitation. So next method for grain refinement is the severe plastic deformation. So what is severe plastic deformation? So it is the all other processes which we studied earlier are the liquid phase process, but the severe plastic deformation is the solid state grain refinement mechanism. Solid state mechanism of grain refinement. In which a part is subjected to severe plastic deformation to a much higher level that lead to dynamic crystallization. So due to the severe plastic deformation SPD, the density of dislocations is very high, and due to high dislocation density, the strain energy stored in the part will be very high, that lead to rearrangement of the dislocation, leading to the dynamic recrystallization after the deformation process. In the dynamic recrystallization lead to the grain refinement, means very high degree of deformation. So there are different processes to provide the severe plastic deformation. First is the high pressure torsion. And equichannel angular pressing. Means ECAT, AP and HPT. In both of these processes, means high pressure torsion and equichannel angular pressing, the severe plastic deformation is provided by shearing force with no change in shape. Or sample dimension, means the sample dimensions are maintained during this high pressure torsion and equichannel angular pressing. Next method is the cyclic extrusion compression, means the part is subjected to extrusion compression cycles again and again. Fourth is continuous cyclic bending. Fifth, next is repetitive corrugation and strengthening. And straightening. In repetitive corrugation and straightening process, a sheet of material is bent by a groove. Then the same after that bending process, it will straighten out. So the repetitive corrugation and strengthening process lead to the severe plastic deformation of the sheet. So these all three mechanisms work with the SPD by large accumulation. Accumulative strain through repetitive deformation. Means the strain is accumulated by repetitive deformation. Next method are accumulative roll bonding. In which deformation by rolling passes on stacks of pre-rolled sheets can be done at a high temperature. Rolling passes on pre-rolled sheets at high temperature. Means the part is rolled, cut it into the sheets, then the stacking of those sheets are done, and again stack of the sheet are processed through the rows that will lead to the bonding between different stacked sheets interfaces. So this is done at the high temperature. High temperature is required for the bonding of different sheets. Means this part is rolled into thin sheet, then this will stack, cutting by stacks, that will again lead to rolling. So accumulative roll bonding. And the next process is the friction stir processing, in which a tool is passed through a part in a rotative in the torsion moment. So the friction torsion and forging friction torsion and forging at the same time lead to grain refine first lead to the plastic deformation, very high plastic deformation locally, and the grain refinement. So the Grain refinement for the friction state process material will have the different types of refined grain regions. Means in this region the grains are very fine. Near this there will be thermomechanically affected layer, affected region. Then far from that, this will be has means heat affected region. And this will be base material. So in the base material the grain size will be high, and as we move from the base to the heat affected zone, thermomechanically affected zone, and the friction state process zone, the grain size will decrease significantly, and significant decrease in grain size. So how the grain refinement process happens in the severe plastic deformation process is can be explained by the dynamic recrystallization process. Dynamic recrystallization, that is divided into three types. First is the continuous dynamic recrystallization, second is discontinuous dynamic recrystallization, and fourth is the geometrically discontinuous recrystallization. So in the discontinuous, so the dynamic recrystallization process, discontinuous dynamic recrystallization process consists the high strain buildup, that has the high dislocation density inside a particular region. Means the deformation is only localized to a region, means the regions near that localized region will have the less dislocation density. Means this is so there will be, so at the interface the strain gradient will exist that lead to the formation of subgrain boundaries by the rearrangement of dislocations. While in the continuous dynamic recrystallization that happens in the high stacking fault energy materials like aluminium alloys, has the stacking fault energy of 200 millijoules per meter square. So that lead to the rearrangement of dislocation near the subgrain boundaries, leading to the formation of high angle and low high angle. So the subgrain boundaries formed in the discontinuous dynamic recrystallization has the low angle grain boundaries. In continuous dynamic recrystallization, the low angle grain boundaries transforms into high angle grain boundaries by rearrangement and rotation of dislocations. Rearrangement of dislocation and rotation of grain boundaries. So in these pictures, the severe plastic deformation in the different process, deformation by shear, are shown as the deformation in different passes by the rotation lead to the different orientation of deformed regions. Like in this process, like root A leads in that pressing with no rotation. BA, in the root BA process, the part was rotated 90 degree in alternate direction between passes. In BC root, the rotation of 90 degree in same direction between passes is done. That lead to slip in first pass is cancelled by slip in third pass. That I will explain in a while. In the root C, the 180 degree rotation is done between passes that lead to that is redundant, means direction of shear is reversed on each pass. So in the orientation here we can see in this table, like for root A, in the xy plane, the deformed plane is shown with the number of passes. So as the 90 degree rotation in the different in the alternate direction lead to the, so in the x direction the thickness will reduce, while in leading to the decrease in thickness in y direction also, while in z direction there will be no shape change. In root BA process, where the in the A root, there will be no rotation will be done, means the same rotated part will feed into the next pass with the same direction. In the root BA, the 90 degree rotation with alternative direction lead to different orientation of slip planes, deformed regions. Similarly for BC, the deformation orientation is different. So in these pictures, grain refinement mechanisms it's shown. So in the first picture, as we can see that the dislocation density is very high in one grain, while the neighboring grains does not have any appearing dislocations. So the strain gradient exists in this material, so that this is a case of discontinuous dynamic recrystallization process. While in the second process, there is can be of continuous dynamic recrystallization, because there is no accumulation of dislocations in one grain. While for the next picture, if we zoom in, we can see the subgreen boundary formed in a one grain. So this is subgrain boundary formed by the accumulation of dislocations because of the stream gradient that lead to and with time, if the recrystallization process proceeds, the complete complete dividation complete dividing of the grains happen because of the formation of high angle grain boundaries. Means the sub angle grain, this is low angle grain boundary that will form the this is the high angle grain boundary. That's why we can see the contrast between these two grains. So how the low angle boundaries and high angle grain boundaries form in a microstructure. So here we can see in the EBHD micrograph, which is the best tool for finding the high angle grain boundaries and low angle grain boundaries and subgrain boundaries. So in this, the grain boundaries are map is imposed on the image quality map, in which the red greens we can see is denoted by the subgrain, which has the minimum misorientation angle of 2 degree and maximum up to 5 degree. So the different red boundaries are seen, can be seen in this picture. So at the some point it is converting into the green line or green or blue line. Blue line is the high angle grain boundaries, whereas the green line is low angle grain boundaries. Means with the rearrangement of dislocations, the subgrain boundaries transforms into low angle grain boundaries, and the further rearrangement of dislocations and rotation of grain boundaries lead to from low angle grain boundaries to high angle grain boundaries. So the transformation can be seen. So means in this grain, if we see, so this will initially the grain was a single grain, but due to the formation of subgrain boundaries, it is divided into two grains, while the subgrain boundaries also transforming into the low angle grain boundaries slowly. That is shown by this transformation of red to green. So the today's session discussion is over. We will continue in the week 9 for the further session. Thank you.